Everybody. Wanted to give you a brief rundown on my visit to the Smithsonian American History Museum. We saw a little piece of the ENIAC, and I wanted to give a special shout out to the person who donated their time generously, Peggy Kidwell, for helping me out. And first I wanted to kind of outline a little bit about what we're about to see here. First, a review of the latch. An SR latch is shown on the lower right. The tricky bit of the SR latch is you don't assert both set and reset at the same time, or else what will happen is you'll cause a race condition. You can implement the canonical latch form here, which is in NOR gates, but could be used just as easily in NAND gates, using a electromagnetic system such as the relay. Relay is characteristic of many of the early computer devices. We've seen it in the Mark I Harvard computer, also in the Conrad Zuse machines. Most of the large Bell Telephone Laboratory machines all used relays. But there were electronic mechanisms for implementing the switches, and they ran way faster. If the switches were running at several hertz, these systems could go from 100 kilohertz out to 500 kilohertz, depending upon whether you had well-conditioned thyrotrons. This is what you call a triode. It has three elements. It has a cathode, a grid, and an anode. And the grid serves as a gate of power that goes from the cathode to the anode. When the cathode is replaced by simply a filament, and then you have nothing more than a filament and an anode, the filament can be used as what they call a hot cathode, and that's a Fleming valve, or a diode, which was originally used by Sir Ambrose Fleming when he was acting as a consultant for Samuel Morse to improve the sensitivity of the transatlantic telegraph. Here we see the cross-coupled grids being used just the way the cross-coupled bases are being used in the transistor or semiconductor implementation, which we see on the upper right. And of course, that can go at many megahertz. So no matter how you implement this, you can still look at the canonical latch in the lower right corner and know that logically it's the same. But implementation's important, and one of the things that we see in the patent is that the two different triodes here on the left are combined into a single envelope called the dual triode system. The dual triode, which is commonly available in the 40s, can be implemented with a single glass envelope, and it can have its own filament for each one of its cathodes. Up here in the upper left corner, we can see another interesting looking glass envelope. That's a neon bulb. There were no LEDs back then, so people used little glass envelopes filled with neon, and they would proceed to emit visible light just the way an LED would, only they worked at perhaps between 50 and 100 volts. So here is a cleaned up version of the same patent diagram, only now we can see the cross-coupled grids for the flip-flop arrangement. Just the way we see it here with two separate triodes. And now we can see how we can create a 2-bit counter. Here are the neon bulbs in the upper corner. Here's 115 volts coming in and 110 volts on the other side. So instead of running 0 to 5 volts, these things could run from minus 115 to plus 110 volts. And that's really quite something. The typical way you would see these things, and they're quite large actually. This is the 6SN7, which is actually used in the ENIAC. We'll see a picture of that shortly. Here's a neon bulb in the lower left corner. And here is the TR2 implemented by IBM. This is a single tube implementation of a flip-flop. And there's a more modern 12AU7, which has completely obsoleted the 6SN7 over here in the center. The accumulator is based in a binary coded decimal, and that's being used as a shift register inside of ENIAC, so that's a serial accumulator. And you can study that in your digital design courses if you like. And then this is the full-blown ENIAC. This is 27 tubes, and there's a wide variety of tubes available. There are tubes for cycling the ring when the accumulator is used for transmitting a number, for adding or subtracting. There's gates for receiving pulses when the accumulator is receiving. There's 4 tubes for pulse standardization and driver tubes to drive the ring on any operation. There's a gate for control and carry initiation. And we'll also see, because it's using BCD, that it needs to use what's called 9's complement instead of 2's complement, which you might be used to if you're dealing with binary. There's gates for synchronization and timing. And what we see here is the basic counting circuit used in ENIAC. When we look at something like this, where we see all these extra tubes, we go, what are they doing? What do they need all these tubes for? Well, there's extra tubes, another 4 tubes used for flip-flops and associated gates for remembering when a carry is required and for implementing the carry. There's really quite a lot of extra stuff going on here to get the implementation going. And what I'd like to do is play a little video for you. Let's see if we can get that running. And here we go. So now we can see they laced the wires with wax threads and did breakouts. They did a very neat little bus over in here. Here's your 27 tubes on the right, and you can see over time they had replaced them with several different brands. Some of them look way more modern than others. And they did a rather neat job, I think, of making this module. And what you can see over here on the top is that there are several extra tubes which are being added. They're not all the same, and they're used for the variety of elements for signal conditioning, including a high-power output buffer to permit a connection to different accumulator transmitters from the single number transmission bus. There's also amplifier and gates available for the single carry, and the same is true for the accumulated carry. So that's my review of the ENIAC. If you like my little video, please give me a thumbs up, and if you really like it, you might like to see more of these videos, support me on Patreon. Thank you. Bye-bye.